from me to you at home, and I'm very happy that you chimed in again for this month's version of Astronomy on Tap, and on the usual suspects for all the social media you see here, but if you're not new here, you've probably seen that before. So also let me go through something you've seen before if you've attended. Please interact with us. There's the YouTube live chat. We have two dedicated person, Maud and Ivalo, to host you today in the chat and answer all your questions, or just give the questions directly to the speakers if you have a question, specifically for what you will hear today. So that would be very nice if you also could say hello, hello from me, hello from the team. And then, as usual, we have a quiz. This time it's the March quiz, and you can find it under the link. It's probably also in the YouTube description, as always. And we're very thankful for our sponsors, the SFB 956 for Cologne and Bonn, and also the Tai Chi Center here in Bonn. So thank you for that, and I hope you sponsor us also in the future. And what you will see today is not only my face, which is kind of happy face today because the weather in Bonn is actually awesome. We have 25 degrees outside, and if you're from Bonn, you know that. But if you're from a bit farther away, I hope you have also great weather as we do now. So that's why I'm a bit more happy mood. And then when I look at the speakers we have today, my mood rises up once more, because the one advantage of doing this, not in the pub, but here online on YouTube, is that we can invite literally everyone. And that's what we did. We invited Yvette Cendes from the Harvard-Smithsonian Center for Astrophysics, and also a friend of mine. We did the PhD here together in Bonn, Dr. Victoria Yankelevich. And then she's the second speaker. She will tell you what pancakes have to do with the universe. No spoiler for the first talk, because we will start right away, and Felix, our moderator, will guide you through the event. Thank you.
Okay, thank you, Sandra. I hope you can hear me well. So as she already mentioned, we have awesome talks today, and I will be your moderator for today. So yeah, let's get right into it. So our first speaker is Yvette Cendes. She got her PhD from Leiden University and is now a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics, where she specializes in radio signals from gigantic space explosions, ranging from supernova to star-eating black holes. She's also known to many as Andromeda 321 on Reddit, where her Astronomy Here comments have been read by millions around the globe, and has also published articles in various media such as Scientific American, Discover, and Astronomy. When she's not researching or talking about astronomy, Yvette enjoys geocoaching, traveling, cross-stitching, or planning for what she politely calls galactic domination. And yeah, I think she brought some really exciting science today. So welcome, Yvette.
All right, thank you very much. Can you see my title slide here?
Yes.
Okay.
I can see it. So yeah, you can go ahead, and I believe you will talk about like these gigantic space explosions.
That's right.
Mentioned, right?
Yep, that's right. Thanks very much for the intro. Yes, I'm Dr. Yvette Cendes. Welcome to the Center for Astrophysics. You know, now that I can just bring my office straight to Bonn, where it is unfortunately 8 degrees. I just checked outside, so our spring is a little behind you guys. But anyway, until the spring shows up, I'm going to tell you guys about supernovae, which are the biggest explosions that we really know of in the universe, which is when a star explodes at the end of its life, when a very massive star dies. We call it a supernova. I'm going to tell you guys a bit about how this sort of event happens, what I do when I study them, and I'm going to tell you guys what would happen if one of these went off in our galaxy and its light reached us tonight. What would that be like? So to begin here, I am going to show you guys, you know, this is if you go out of Bonn, if you don't have much light pollution, and look up right now in the evening sky, this is what you would see if you look out, if you know, a little bit. So in the middle here, what you have is the Milky Way, the little band of stars here, but then you have, this is the constellation Orion. So a lot of you guys know Orion's belt. It's 3 stars that are in the winter sky, and they make up part of Orion, the constellation, Orion the Hunter. And just to go through a few of the stars that we see here, what you see in the upper left shoulder, which is a little bit of a reddish star, is called Betelgeuse or Betelgeuse. And then you have the star Rigel, is the lower right foot star. And then the other nice thing is if you take Orion's belt and follow it down, you will actually get to Sirius, which is the brightest star that we have in the sky. And these are all interesting stars because, you know, obviously they're all bright stars in the Northern Hemisphere, but they're also all stars at different stages of their lives, different lives, and they can kind of tell us how stars form. So these stars are all, you know, different brightnesses, different distances to us. But if we take another view, what we see is all these stars are very different in their sizes. So Sirius, as I said, was the brightest star in the night sky. So actually, to begin with, I want to point you to the upper left-hand corner. We have the sun, which, you know, we think the sun is big. It's actually a very tiny star compared to some of the other stars we see in the sky. Sirius, you know, is the brightest star in our sky. It's only about 8 light years away. So when we say light year, that means the distance it takes for light to travel in outer space to reach us. So if you were a beam of light and you left Sirius, it would take about 8 years for you to reach us. Rigel is a much bigger star, and it is a few hundred light years away from us. And Betelgeuse is by far the biggest star of all the stars that you can see in the constellation of Orion. And it is a few hundred light years away from us as well. And Betelgeuse is also interesting because we think it's a star at the end stages of its life. And it's also a very massive star. So it's going to end its life in what we call a supernova. So what happens when you have a supernova explosion is a star basically shines. It's burning hydrogen into helium, fusing that in its core. And eventually it runs out of fuel. And if a star is 8 times bigger than the size of the mass of our sun, so you can't, if you're a star the size of our sun, you do not end in a supernova. Basically what happens is you have this gigantic explosion that happens when the star collapses in on itself. It can no longer fight the gravity that is pushing it outward. And the cool thing actually about this, the reason we know about supernovae, is we've actually seen them for thousands of years in history. So for example, in AD 1054, there was a supernova. It was, actually, they didn't call it a supernova. They called it a guest star in the sky that was recorded by Chinese astronomers who were very sharp-eyed people. It was a guest star in the sky that peaked in summer. So it was so bright that you could read by it at night for about a month. And then it was actually visible for 2 years in the sky before it faded away completely. And this was actually seen not just by Chinese astronomers, but by astronomers around the world. So Japanese and Arabian astronomers also saw it. We also have reports in Europe and Chaco Canyon, actually in New Mexico, USA. There are petroglyphs that Native Americans drew, which we think are actually representations of this supernova. And the cool thing is Chinese astronomers were very good astronomers, and they wrote down the coordinates for where they saw this guest star in the sky. And these days, if you take a telescope like the Hubble Space Telescope and point it in that direction, what you see is this giant thing that to me looks like a big explosion happened there. And it's about 10 light years across. So as I said, you know, it's bigger than the distance to the brightest star in our sky is basically what the remnants of this gigantic supernova explosion looks like today. This is called the Crab Nebula. Now, to continue though, so, you know, we've seen these bright stars throughout history. The trick is though, we haven't actually seen ones in our own galaxy since 1604 AD was the last recorded supernova. It's called Kepler's supernova. And yeah, so that was actually before the invention of the telescope. So the closest supernova that we've seen, that's to sort of see how that's been going on, is called supernova 1987A, which occurred in 1987. It was the first supernova in 1987. So astronomers are, of course, very creative in their naming here. And it took place in a satellite galaxy to our Milky Way, so 170,000 light years away. We're going much, much further outside of our own Milky Way galaxy. And what you can see here is basically there was a star that was the first time we actually saw a star and then it exploded. And this is the closest example we have to a supernova to Earth. All other supernovae have been much further away from us that we've observed. So I'm going to tell you guys a little bit more about supernova 1987A because this is like where we've learned a lot about what this process is like. And also I've actually done some research myself on supernova 1987A. So this is a video. Basically, we take radio observations with radio telescopes. It was a southern hemisphere object. So this was a radio telescope in Australia. and basically just check in over time to see how the supernova is evolving and how it is getting bigger and all sorts of things like that to see how the supernova expands. So the telescope did not exist in 1987. It got built in 1990 or so. And what you can kind of see here is there's a shock wave expanding outwards, and it is just hitting all the material that was surrounding the star supernova 1987A before it exploded. And when this happens, you basically have the shock wave is going outward and electrons are spiraling in magnetic fields. And that's just creating this radio emission that we see. And the more stuff it hits, the brighter it gets. You can also then start studying things like, okay, it starts getting brighter on the left side and then it gets brighter on the right side. We can compare this to, you know, Hubble Space Telescope images and other wavelengths like X-ray to sort of see how this system is evolving and what happens after the initial supernova explosion happens. Also, just because this is cool, and if you want to look at something in particular, I said I do cross-stitch as a hobby, and I actually cross-stitched the radio evolution of supernova 1987A as a gift for my PhD advisors. This was the first figure from my scientific publication that we did together, and Astronomy on Tap feels like a really cool place to show it off. So I'm just going to show you guys really quickly. This is actually 100% accurate astronomically. So if you're looking at the picture on the right, these are the coordinates. So you can use the scale to see how it's expanding. You can see this little thing in the upper left corner is actually called the beam size. So that's the rough resolution that you have for how this supernova resolution that you have from the radio telescope. And you can see that it started smaller. It definitely got bigger over time. And I should point out, by the way, my PhD advisor, he also loved this because he actually did the first few panels himself for the radio observations for his own PhD thesis. So supernova 1987A is a very cool object because, you know, it's the PhD project that keeps on giving. Yeah, so to kind of carry on though, so I was telling you guys before, you know, so okay, we're talking about these stars in Orion and sort of how they're evolving and what is going on there and things like that. So I was just going to spend a few moments first telling you guys, because up here is Betelgeuse. And I think a lot of people have heard about Betelgeuse recently because it was in the news because it started dimming and people were like, oh my God, Betelgeuse is dimming. It's a star that's supposed to go supernova. Does that mean Betelgeuse is about to go supernova? And the media got very excited about this. I don't know a single astronomer who I ever saw who thought that this dimming was related to Betelgeuse being about to go supernova. Because, you know, it's a star, when we say almost at the end of its life, there's still thousands of years that could probably pass between, you know, the explosion of Betelgeuse and the end of its life. But the thing is, you know, astronomy, it's not always an exact science. What I mean by that is because we can see the star is at the end of its life, but we don't know exactly what is the final moment for when a supernova explosion happens. I can't like point to a star and then be like, that star is going to explode tomorrow. It's not that precise. I can say, you know, within X number of years, it's definitely not as likely to explode as Rigel, which I can also see, or Sirius, or any of those other stars. So as I'm saying, it's at the end of its life. That's kind of what we're talking about. Like, not super likely, but you really don't know. And in astronomical senses, when these stars can live for millions or even billions of years, you know, it's very soon for the overall length of that star's life going to explode. To kind of go into, though, what's happening with Betelgeuse, what happened when this dimming happened, so this is January 2019, it was, you know, glowing at its normal brightness, and then it started to dim, and people actually did look with ESO telescopes to see what exactly was happening. Betelgeuse is so big, it's actually the only star you can resolve in the sky. It's not just a point source, like you can actually see a little bit about its shape. And what we could see is it actually did, you know, change shape. Okay, did the star physically change shape? What's more likely is there's actually a dust cloud that got ejected from the star, you know, in the period of, you know, around December 2019 when this dimming happened. The thing to also point out, though, this is a common thing that stars do at the end of their lives. They lose a lot of mass here and there. I mean, as I said, there was mass around supernova 1987A that got hit by the shock wave and then lit up in radio. So this is something, it's not that unusual for this to happen. I will point out, though, so Betelgeuse is now, it's roughly at about its previous brightness, but it's also a periodic thing. This dust cloud is still there. It's still rotating around the star. There's actually a prediction that within the next month, we're going to enter another period of dimming for Betelgeuse. So, you know, if you hear it in the news again, Astronomy on Tap is the first place you heard that this is probably just something that Betelgeuse is doing at the end stage of its life. But anyway, okay, now that we've said that, what would happen if a supernova were to go off in our galaxy and its light reached us tonight? This is not a very common thing. For the record, we expect a galaxy of our size to have about 1 supernova per century. But 1 supernova per century, we haven't observed one since the 1600s. There is a good chance that, you know, we will see a supernova in our lifetimes. So the first thing to emphasize is we're not going to die. The reason I say this is because people are always really nervous about this. They think that, oh, giant explosion. I mean, giant explosions only really affect you if you're next to the supernova explosion itself, right? These stars are very massive. We can see them very far away. For a supernova to actually hurt you, you have to be well within 100 light years of it. If there was a star about to go supernova within 100 light years of us, we would see it and we would know that, oh, okay, that star is about to explode. So we don't think that a supernova explosion is going to get us. The other thing that's kind of cool about supernova explosions is you actually know if one is coming. You have a few hours advance notice if there's going to be a supernova. And the reason is thanks to these really ghostly particles called neutrinos. So the way neutrinos work is they're kind of they're fundamental particles like electrons or something like that, you know, like what makes up your atom, but they don't really interact with much and they're just everywhere and a lot of things produce them. So to give you an idea of how many neutrinos there are, if I do a thumbs up, so like if you do a thumbs up right now at the screen, every single second, 100 billion neutrinos are passing through the tip of your thumb. Obviously, they've been doing this all your life. You did not know about it till now, so they really are not affecting you in any way. A supernova explosion, though, gives off as many neutrinos as there are atoms in the sun. So if a neutrino takes off a place really, if a supernova happens really nearby, you would detect a stream of neutrinos from it. The way you detect neutrinos, by the way, this is a neutrino detector. These are little detectors. You fill this up with water. For a sense of scale, this one is in Japan, and those are people in a boat, to give you a sense of scale of what a neutrino detector looks like. And basically, these detectors have an alert system called SNews. You can go online and sign up for this because basically, if all the neutrino detectors on Earth suddenly detect a huge number of neutrinos, then we would know about it, and you would actually have a few hours advance warning. The way this works, and we know this because we detected neutrinos from supernova 1987A, even though it was, 170,000 light years away. That was the first time neutrinos were detected from outside of our solar system. Basically, when the star dies in its core, these neutrinos all get produced. And they're not, as I said, really interacting with any of the material in the star. They're basically just going to escape immediately from the center of that star. On the other hand, though, if you have light, light interacts with things as it's going through that material. And it does take a few hours for that light to escape the star, like just all the sheer amount of stuff between the core and the outer bit. So it's not that the neutrinos are traveling faster than the speed of light. They're just not interacting with the normal matter. So you will actually get a neutrino alert a few hours before you will actually see light from the supernova. Anybody can sign up for this in the world. It's called SNews. Neutrino Alert System. And then you will get an email if they're like, oh my God, we just saw a ton of neutrinos, you should run outside and see what that's like. So just to wrap up, let's say you signed up for SNews and you're like, oh my God, I just saw this alert. I am going to run outside and see what exactly I'm going to see because I might, see something nobody's seen before in our lives. And so, if you get this alert tonight, run out. And then, you would see something like this. It would be a guest star, the first that anybody has seen with their own eyes in our galaxy in hundreds of years. Something, potentially bright enough that you can read by for weeks and weeks. And, this is what we're talking about. We're talking about supernova, the biggest explosions that we have out there. Thank you very much. I'll take any questions.
Well, thank you very much, Yvette. So this was really very interesting. And there are actually a couple questions from the chat. So the first one is, they want to know the difference between a super and a hypernova.
Okay, so this is one of those things that I don't really know astronomers who use the word hypernova very much. So we have other types of classes that we use for supernova. I'm pretty sure hypernova is if a gamma ray burst comes out of the supernova, then it's a hypernova, but I'm not 100% certain. There is an interesting new class, though, I will say, of supernovae called superluminous supernovae, and these are basically just even more energetic supernovae, even brighter ones. But we've seen them, you know, many, many light years away, like hundreds of millions. We have not seen any of these up close yet. So.
Okay, maybe as a follow-up from myself. So if there were to be a gamma ray burst connected with the supernova in our galaxy, could that potentially be, if it directed at Earth, could that be dangerous in some way?
Okay, so yes and no. So this is like one of my pet peeves in astronomy. So gamma ray burst, for those who are not aware of the term, it's basically a burst of gamma rays, which is really the most energetic thing you can happen. And some supernovae that are particularly massive will create a gamma ray burst. It's basically a beam just like to Earth, a few degrees, like so let's say 2 degrees or so from the poles of this supernova. And those are much more rare. We think there's about 1 every million years for a galaxy of our size will have a gamma ray burst that comes out of it. So the thing about those is, yes, if there's one directly pointed at you and you're within like 4,000 light years, then yes, that's very bad because it will basically fry the atmosphere of Earth. And you'll often see this in documentaries like people scaremonger. That's another one though, like those are the even more massive stars. So within that radius, there's still just not that many of them. And the ones that we can see, all of their axes are actually not even pointed at Earth. So even if they explode, it's not going to affect us. So right now, like death by gamma ray burst is just not a very serious concern. So that if it happens, but really not likely.
So we can celebrate, so we're not going to die by that.
Yes, indeed. We're still not going to die, is the take-home message here.
That is good to know.
Yeah.
Another question is, what will be the remnant when Betelgeuse goes supernova?
Oh, that's a good question. So I didn't have time to get into this, but there's 2 types of things you can leave behind when you go supernova, either a neutron star, or if it's very big, the neutron star will collapse further and leave a black hole. I believe Betelgeuse is not big enough that it will create a black hole. I believe it would just be a neutron star at the center of that. I'm not 100% certain. Also, I should note that they finally, within the last year, think they found the neutron star at the center of supernova 1987A. So this is like, you know, very new. Most stars, even that go supernova, though, do not create black holes. You have to be very big for that.
Okay. There's another question. You mentioned that neutrinos don't really affect us. So do they affect any physical systems that we observe when they interact with the atmosphere or the Earth in some way?
Oh, that's a good question. I mean, we can detect them, but it's really hard. So like, you know, they do interact to the level that you can detect neutrinos. Basically, they'll hit other particles and create little flashes is what you're looking for. So you will get some radiation from as they hit the atmosphere, but this is just such a minuscule thing, like 0.001%. That's probably even too high. I'm not an expert in what exactly the percentage is there, but yeah, so they don't really affect us much at all.
Okay. We have one last question that is partly scientific. It's do you create more scientific embroideries? And they say it's a fascinating aspect of this hobby.
Sure, actually. So let's see here in my office. Yeah, so this is, I didn't get to talk about tidal disruption events, but that's when a star gets too close to a black hole and tears it apart. And this is one that I studied called Swift J1644 plus 57, and I keep on my desk. So this is the radio picture. That's the emission. It's so far away, it's just a point source. It's not as pretty. That's the beam size. And yeah, that's another one that I keep around for events like this, because why not? Where else are you going to keep it? So
this is so cool. Can we buy them?
No, it's just a hobby. Let's put it that way. But I always joke that, you know, I have given these to collaborators. So if you have anything fun to collaborate on, let me know and we'll see what happens.
Okay, I will keep that in mind. Okay, then thank you again for this awesome talk and the great answers to the questions.
Sure thing.
And yeah, I think we can. Oh, okay. I think we're getting one more question in. Did I forget something? There. Maybe it got lost somewhere. So there's one more question that we can maybe try to answer. Is there an even bigger candidate for a supernova than Betelgeuse?
Yes, actually. So this is another, talks are only so long. I actually don't think Betelgeuse is the most likely star about to go supernova in our galaxy, but it's a southern hemisphere star, so you probably haven't heard of it, called Eta Carinae. And Eta Carinae actually did this giant mass loss, got super bright in the 1800s. It was like the third brightest star in the sky, then completely disappeared. And that's actually much more likely to explode. It's much bigger. We're not quite sure because there's a lot of dust between us and it, but it's probably about at least 50 times the size of the sun. As I said, that's big enough. A gamma ray burst will happen, but you can see the distribution of the dust. It's definitely not pointing toward us. So Eta Carinae is the most likely one. The only trick is if that goes, you're going to have to buy a ticket to the southern hemisphere to see a supernova with your own eyes. So.
But anyways, such supernova would be around for some time, right? So
you'd have
some time to travel down there.
If Eta Carinae goes, you'll have, as I said, I mean, the first month is the brightest, or first few weeks, but it will be in the sky for years to your own eye. And that's basically, people will study that for the rest of our lives for sure, if that happens.
I think I will go and sign up for that neutrino mailing list. So
it's pretty fun. They've never had a false alarm yet, so they're either doing a good job or not. Like, we'll find out. So
I will check it out. Okay, then thank you again, Yvette.
Yep, sure thing.
Okay, so let us move on to our next talk, our next speaker. So our next speaker is Victoria Yankelevich. She studied for her bachelor and master degrees in astrophysics at the Southern Federal University in Rostov-on-Don in Russia. And in 2015, she moved to the Argelander Institute for Astronomy in Bonn, where she also met many of us there. And she did there the PhD in cosmology, which she earned then in 2019. And then she moved to the Astrophysics Research Institute at Liverpool John Moores University in the UK, where she currently works as a postdoctoral research associate in theoretical and computational cosmology. So welcome, Victoria.
Yeah, thank you, Felix. Let me share my screen. Yeah. I really hope it's going to work.
I can see it. So yeah, you will talk about the universe in a pancake. I'm very looking forward to what you will tell us about the universe today.
Thank you, Felix. So yes, the title of my talk is The Universe in a Pancake. But today my talk is a little bit unusual style, because at the end of the talk, you will learn something new about our universe, but also you have a short guide on how to create a universe in your own kitchen. So you have a great idea what to do, what to make for dinner. So yeah, let's start. The universe. Cold and hot, dark and shining, structured and chaotic. But in any case, it's absolutely stunning, mysterious, and looking for our attention. This is a picture from famous Hubble Space Telescope, and it's called Ultra Deep Field Survey. So all these shiny dots with all our galaxies, long time ago and very far away. We, in astrophysics and cosmology, we know how our universe was born. We know the origin of it. But nevertheless, we can't really reproduce this process. We have now a huge supercomputers where with numerical simulations, we can reproduce a variety of things. We have enormous amount of telescopes, ground-based telescopes, telescopes in orbit, flying telescopes. We can do a big variety of observational data. We can do a huge amount of things, but we can't reproduce a moment of the origin of our universe in the lab, like you can do it with our experiments. However, what if I tell you that in some sense, and some parts of it, you actually can reproduce, and you can reproduce it at your own kitchen. And today I will show you how to do it. So you will need several things, but basically you will need some products which you usually use to make a pancake mixture. And let's start our short guide on how to create universe in your own kitchen. So first of all, we need to start with a Big Bang. According to the modern cosmology, our universe, the first moment of originated of it was a Big Bang. But it really is how it sounds, a huge, huge baraboom. So what is why? Safety rules. First of all, please do not reproduce Big Bang in your kitchen. Really, especially people in Germany, people, you would never get your calcium back, never ever. It won't be possible to explain to your landlords what happened in your kitchen. So Big Bang we have only in slides. And then, so what happened? 13.7 billion years ago, the tiny cluster, the singularity of matter and energy start exploring. As you can see it now, you see the dot in the screen. It's like in the middle of the space. But in that moment, the terms of space and time, they didn't exist yet. It was no space and time in how we see it. So this dot, it wasn't in any space because it was no space. All the space and time were inside this dot. And then it finally exploded. And at this moment, the clock, the time of our universe started ticking. And together with the expanding of the sphere of a Big Bang, it was also expanding the matter and the space itself. And even this process of expanding was very short. It was 10 times minus 32 seconds. But at this tiny moment, our universe expanded millions of times. And it was very, very rapid, extremely fast. And we called this part inflation. So yeah, please, also again, safety rules. We are also not repeating inflation in our kitchen, because if you start inflation in your kitchen, well, you will need to go not only outside your kitchen to reproduce the size of inflation, but you also need to go further than Bonn, Germany, and all our planet. So again, inflation and a Big Bang only on the screen. What was in the end of inflation? We already have our matter, our space, and we had a soup of tiny elementary particles which were interacting with itself. And there were several stages of how these particles were combining to each other. And here in the diagram, you see it was several processes. I combined all of them at once. And now you see why. So what do you have at the beginning? You have quark-gluon plasma. So it's a tiny, tiny particles, interaction between, and they start combining themselves in baryons, also known for us as proton and neutrons. And now we finally can come to our pancakes. So what you do when you want to make a pancakes? You take a big bowl, and what you do first? First you cut an egg and put an egg inside, then mix it, then you put the sugar inside and you mix it. Well, sounds like quark and gluons, right? Because already an egg and sugar, we start combining together, you mix it, you know, change the color, maybe a bit of foam. And when we already have baryons, our baryons start combining with our electrons. And then we start having neutral hydrogen atom. So at this moment, we start having atoms from which we all are made. Not only our pancake mixture, but also us. And to come back to our pancake mixture, so it's the same. You already have a bowl with your egg and sugar, and what you add? You add milk, you add flour, you add a bit of oil, a bit of baking powder, and you mix it, mix it, mix it. And when you have at the end, you have a liquid, right? Doesn't matter how good you mixed it. You even could put it in a blender. It still will have some tiny clumps inside, some air bubbles. So it will be almost homogeneous, but still it will be some tiny, tiny fluctuation of things. And this is a key feature. Because as soon as our baryon and electrons combine together and organize a neutral hydrogen, the universe became transparent for photons. And in this moment, we finally can see a first picture of our universe, a picture of cosmic microwave background. For most of you who are following Astronomy on Tap, you've seen this picture 10 times at least. It's very popular. We're all posting it because it's really, really very important for us. So what you see here is the first picture, like according to the age, is the picture of earliest universe as we can make. And colors here represents the difference in the temperature. And even you see by colors, it's quite a difference in blue and red. But by value, it's tiny, tiny fluctuations. The difference in these colors is like 10 times minus 5. But difference in the temperature also means difference in the density. So it's like our pancake mixture. You can mix it again as much as you want, but still it will be some tiny clumps, like here, red spots. So for example, if you pick a small spot and you zoom it out, and then you put it in a time machine for like 10 billion years, you will get galaxies, these huge, huge monsters which we observe today. They all grew up from these tiny fluctuations of matter from a cosmic microwave background. And the same thing is happening with a pancake mixture. When you pull it out on a pan, you have a flat surface, but you still have these tiny clumps and tiny holes, which will later evolve in time as soon as you turn on your stove. But why this picture is so important for us and what we actually can learn with it? Why we still keep looking, even we have it for years now already? The thing is, we assume that all the process in nature are random. It's a kind of, it's default, you know, it's something for us which you even don't think about. So for example, if you flip a coin infinite amount of times, you get 50% one side, 50% another side. If you roll the dice millions of times, each side of the dice will pop up 1/6 times. And we even don't, you know, we don't even think about this because it's so deep in our brain that if you do things like naturally, the result is random. But what happens if you influence this result? What happens if your coin, well, you know, you slightly tied it from one side, you put, I don't know, something else inside, and in this case, if you flip a coin millions of times, it won't be 50-50 anymore. Or what if you have a dice like from 12 Ocean Friends, a dice which was specially made with some magnets inside and blah, 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 you know, to make them fake. If you roll with dice, you won't get 1/6 for each side, right? But this process had influence from a side. So it's not random anymore. That is why for us, for astronomers, it's very important to know, is the microwave, cosmic microwave background Gaussian or not? Is it random or not? If you look in the squares at the bottom of the slide, one which random, you see it has a bit of different lights and colors, but still, even if you split it in 4 sides, in 4 different cubes, they will be the same to each other. But the one on the right, the non-random, you see the structure. You see the clusters, which is like galaxy clusters. You see things looks like walls, the filaments. You see holes, which we're calling voids. So there is a structure there. And if you divide this big square in 4 small squares, they won't be the same towards each other. So this field won't be Gaussian anymore. And exactly this process we can reproduce in our kitchen. And we'll see how. So our pancake mixture is our CMB. So what you do? You pour out a pancake mixture on a pan and you put it in the stove. And this is how you see the raw pancake. So what do you see there? You see there are some clumps, you see there are some holes, but you just pull it. So it's a random process. And our pancake looks pretty random. So here I showed 2 random pancakes. So it's very, very difficult to make absolutely perfect round pancakes. So imagine all of them around. But if you zoom first one, you see if you divide it in 4 parts, towards each other, they would be the same. And this is a great example of random field. Or if you zoom out with one, you see because it has a bigger holes and a bit more like structured things. But still, if you divide it in 4 parts and compare these 4 parts against each other, they would have pretty much the same number of holes, clamps, and everything. So because the process of how we made two of these pancakes were absolutely natural. It was no influence from the side. It was random. But now we want to make a non-Gaussian process. And here you can use whatever imagination you want to. So I personally tried several variants how to make them not random, how to influence this process. Some of them were a bit less successful, some of them were eatable, some of them not. So I'll present you one which I found the most good as a demonstration. So you take your pancake mixture, you take the same pan, the same stove. But this time, when you pull your pancake mixture on a pan, you put the pan with the angle to the stove. And what's happened? The mixture starts leaking from the top to the bottom, but it's already hot, right? So there is still some mixture on the top. But if you look in a picture, the top part is what? You see there's a huge holes and it's already probably started cooking. But the major part of the mixture by gravity, it all falls down to the bottom. And in the bottom, you have very, very thick layer of this mixture and there's only a tiny bit of holes. So does it look like random for you? No, it's not random anymore. So if you zoom it out and if we divide this pancake in 4 parts, they're not the same. Okay, maybe the top 2 are the same to each other and the bottom 2 are the same to each other. But if you compare the top part and the bottom part, they're absolutely different. The top one is very flat, there are a lot of holes, and it's already started cooking. The bottom part almost doesn't have any holes, it's very thick, and it will take much, much longer time to cook it. So you can try to experiment in your kitchen. Just some small tip. It's when you try to make this pancake, after several seconds, the top part is already almost burnt and the bottom part is still not cooked yet. So it's very difficult to eat this pancake, but as a demonstration purpose, you can play with it. You can try different things. You can, for example, add a bit of some fruits inside your pancakes and mixture it. And first time you just pull it and you have your pancake with some pieces, I don't know, raspberries inside. But another time you pull a mixture and with a spoon, you move very, very fast with small pieces of strawberries, I don't know, to shape of star. And when you fried your pancake, it has a star inside, right? It's not random anymore, but there was some influence. You influence the process. If you come back to the universe, how it might happen? Well, there are different ways how it might happen. So for example, here, when we make our pancake, our pan with a slope, we change, in some sense, we don't change the gravity, of course, but we change how the gravity affects upper part and the bottom part, right? That's why by gravity, the pancake mixture flow down from upper part to bottom part. So in real life, how you can influence our microwave background to be not Gaussian? Well, you might have different space curvature. We might have different inflation theories. There are different ways. So there are actually physical theories which might predict it, not only why it's not Gaussian, but the most important, what was the physical mechanism of it? Because the question why, it's a bit like, you know, it's a kind of debatable, it's a bit more philosophical question. But the question if how it was made, this is a very physical question. And there are things and there are theories which can describe it. But kind of spoiler thing, there is no answer for today. Is it not Gaussian or not? Because up to now studies, it's Gaussian, but we still have some error bars, still people are continuing experiments. So this question is still has to be discovered. So the answers still have to be discovered. And people who are working on TB and other parts of astrophysics, they're really still looking into it. So then what happened later? What later happened several stages. I combined them all and called them structure formation. So as soon as you pour out this pancake mixture, what's happening with your pancake? It starts cooking, right? It became crunchy, it became more a bit brownish, gold, you know, holes maybe become bigger. And the same things was happening with our universe. So after the picture of cosmic microwave background, the structure formation has begun. First of all, it was the formation of dark matter particles. They start to form structure themselves. They start forming halos. And when the baryons, they start, because they interact by gravity with dark matter, they basically start falling down in this gravitational potential. We start to interact with each other, we interact with dark matter, we start making gallows on top of a gallows, they start making their own structure on top of dark matter structure. And then when the first stars and galaxies were formed, then it was the evolution of galaxies and galaxy clusters. And after years and years of this evolution, we see the universe as how as we see today, right? And this is basically how it's happened again with our pancake. After you pour a mixture, you cook it. So it's still evolved. And then at the end, when you take it off from a pan and you put it in a plate, it looks so done. It looks how you look at it now. And the same thing as how we look now in our universe. It's not the final result. Our universe is still evolving. But for us, what we see nowadays, for our lifetime, this is in some sense a final result, final cut. This is what we can and what we should study. And a couple more remarks, what you should take home from today. So first of all, I hope that you can enjoy pancakes on a dinner and you can experiment with it. So please feel free to be creative. But first important thing, safety first. So please, no big bang inflation on your kitchen, no fire, anything. Please be very, very careful. Follow instruction, and then you can enjoy your pancakes for dinner. Yeah, thank you.
Okay, thank you, Victoria. This was a very interesting view on the universe. And yeah, I think despite learning more about the universe, I'm getting hungry when you talk so much about pancakes. So maybe I will have pancakes for dinner and yeah, try to look at it as a universe. That's really interesting. So basically, I can make my own universe evolve.
Exactly, you can make your own universe, and most important, you can create it as you want. You can make it flat, cooked, not cooked. You can really create your own universe and later eat it. Yeah.
Who knows how many different universes are somewhere and we don't know about, right? That stands up to our imagination.
Exactly.
Okay, there's a question from the chat. So please, if you have more questions, please write them. So do you know what caused these tiny fluctuations in the cosmic microwave background in the first place?
So they are predicted by inflation theory. And this is just some, so what was happening is we had some, in the beginning, we had some field which made a transition from one field state to another quantum field state. And this was a process during Big Bang, and this was a process during inflation. And with field transitions and everything, they created these tiny fluctuations. And later, already gravity made the rest of the work, because the thing is, you just need very, very tiny fluctuation, and by gravity, it will grow huge. So yeah, it was, so basically the inflation causes these tiny fluctuations.
Yes, I think that inflation is always a bit unintuitive, right? Because the universe expands so rapidly at the beginning, right?
Well, basically, there is really a huge variety of inflation theories, and to be honest, they can predict many different things. So basically, you have different inflation theory for different questions, for different models. But people who were making all this inflation theory, they also thinking about beauty, and they always say that we think that the most correct model and the most beautiful model is the simplest model. So one of the model which we have now, it's quite simple compared to all the theories which you can build on top of it. It's simple, it's elegant, and it describes what we can see.
Yes, that is true. Okay, so thank you again, Victoria, for this wonderful talk.
Thank you.
And I will then hand over to Sven, who will present the results of the quiz where you could test your knowledge about astronomy. So thank you, and yeah, you give it up to Sven.
Yeah, thank you very much. Let me just share my screen. I hope you can all see it now. Yeah, welcome to this month's quiz. As usual, please send in your solutions. Now we can, of course, not accept solutions after we have already presented them. And yeah, you will notice that this quiz is a bit different than the other ones. But yeah, let's just dive right into it and talk about the most interesting things, which are, of course, the Astro News, and in particular, this question. I mean, okay, this is a personal bias, but I find this fascinating. Namely, something that is regularly used in Star Trek. We thought it was impossible, but now it turns out it's just very, very difficult. And what we're talking about is a warp drive. So a warp drive works in the following way. We all know that you cannot travel faster than the speed of light. Special relativity prevents that. But a warp drive would more or less compress space in front of your spacecraft. Then you travel through this compressed space, and behind your spacecraft, this space is expanded again. That way, you would be able to travel faster than light, although in your own reference frame, it wouldn't look like it. Several solutions for this warp drive have already been suggested, but the problem was that you needed negative energies to create it. And negative energies is something that, while it does exist in quantum physics, you cannot really get large amounts of negative energy. So this was generally not really possible. But now there has been a new paper that actually found a solution where you only need positive energies to create a device to travel faster than the speed of light. I should say two things to that. First thing is, all of this is just under the assumption that general relativity is correct, which so far all the tests we've made have told us, yeah, it is. But we've never really tested this region of general relativity, so it might just turn out to be completely bogus. And the other thing is the energies required are massive. Right now, we would need basically the mass of the entire planet Earth converted to energy to create this warp drive, which, I mean, is not possible for us. But now, faster than light travel has moved from a science problem to an engineering problem, which I think is very, very nice. And it's a very interesting philosophical question, and it has also fascinating implications on metaphysics. So, for example, causality would be violated with something like that. So yeah, very, very fascinating paper and very nice discovery. Moving on to the next question. Oumuamua's shape has puzzled scientists so far, but now a new hypothesis has emerged which claims that Oumuamua is A. So maybe before we dive into this question, Oumuamua is an extrasolar object, and it has a very, very elongated shape, kind of like a cigar. So it comes from outside the solar system, and it looks weird. So what people first said is aliens. And the problem is not many scientists said aliens. But the scientists that say aliens are more interesting to the press than the scientists that offer some boring, mundane information, right? So you probably heard like, yeah, this is aliens, some alien spacecraft or whatever, just because this is a way more interesting explanation that gets picked up by the media. Whereas the reality is probably far more mundane. It's just some fragment of a planet. This would explain the weird shape and the weird behavior that it's doing. And yeah, of course, we cannot rule out alien spacecraft, but we cannot do that with anything, and just claiming it's aliens just because we don't really understand it is very, very far-fetched. Yeah. So the third question, the theory that that an astronaut caused the extinction of the dinosaurs has long been extremely popular, and the last gaps in this theory have now been closed, namely by the analysis of dust from the asteroid. So 66 million years ago, the dinosaurs went extinct, and we found a layer of dust around the Earth that corresponds to this time, this epoch in time. So this asteroid impact has very, very long already been the most popular hypothesis for the extinction of the dinosaurs. But now we actually found the same dust in the impact crater of this asteroid. So this settles it. We now know for certain that this asteroid was actually responsible for the extinction of the dinosaurs. Okay, moving on from the Astro News, we go to the Pictionary, where we have talented artists draw or sketch pictures. And you have to guess what these pictures are. So the first one is just a black circle the size of about 1.8 centimeters, or actually the size of pretty much exactly 1.8 centimeters. This thing is very massive. It is a black hole with the mass of the Earth. So if someone were to, some evil villain, I don't know, were to convert the Earth into a black hole, the entire Earth, this is the size that it would be. Just to give you an impression of how dense and how massive those black holes actually are, right? And then you look at the black holes that are larger than our entire solar system, and it's just, yeah, you can print out the numbers, but it's unimaginable how massive these objects are. Yeah, the second one, if you have listened to Yvette's talk, you maybe recognize this. This is the Crab Nebula, the remnant of a supernova that went up, of a star that went supernova in 1057 AD, I think. Yeah, with a neutron star in the center that illuminates this gas cloud and yeah, makes it glow. By the way, also a really pretty picture in my opinion. Maybe for some desktop background, or can recommend. And the last one, with the hint perfectly balanced as all things should be, refers to something that happened very recently, namely on the 20th of March, if I'm not mistaken, and that is the vernal equinox, the day where day and night both last exactly 12 hours on the entire globe, with exception of the poles. So yeah, very astronomically speaking, quite important day, but for life on Earth, it doesn't really matter that much. So now we go to the last section, which is not movie posters anymore, because we don't have movie posters anymore that we can give you. This online event has taken longer than we had hoped, and we had to come up with a new quiz category, which is common misconceptions. So here we present you something that many people seem to think, some common misconception, and you just have to say why this is wrong and what is the correct answer. The first one is there is no gravity in space. And you actually see that a lot when you watch some videos from the ISS, for example. The astronauts are floating around, right? You see here this astronaut with his tomatoes that are all floating around. He's not a very talented juggler. This is very easy on the ISS. But that is actually not because there is no gravity. Gravity is everywhere. The thing is that the ISS is in free fall the entire time. So think when you're on a swing at the top point of your swing, you're weightless because you are in free fall before the swing catches you when you swing back. That is the same thing that happens on the ISS just the entire time. And it's moving so fast that it's falling, but it's falling and constantly missing the Earth. You can see that here on the right with this little sketch, right? It's falling towards the Earth, but it's moving fast enough that the Earth curves away at the same pace. Yeah, the second common misconception is that astronomers know the name of every star. That is, of course, wrong because so far we've discovered about 2 billion stars in our galaxy. And if someone can remember 2 billion names, yeah, congratulations, I cannot. But actually, most astronomers don't know very many stars. We don't really care about constellations or something like that. Of course, we have an above average interest in the night sky, so we probably know a bit more than the average person, but it's really not that much. The people that care about constellations and stuff like that are more astrologers, and if there's one sure way to offend an astronomer, it's to confuse them with an astrologer, right? So yeah, please don't ask us for constellations that will just embarrass both parties. Yeah, third and last misconception, the seasons on Earth are caused by the distance to the sun. That is actually a very, very widespread misconception that I actually even had to read in a school book. This is completely wrong. The Earth is actually closest to the sun in January and furthest away in July. The thing that causes the seasons is the tilt of the Earth's axis. It also wouldn't really make sense if the distance to the sun would cause the seasons, because when we have summer on the northern hemisphere, we have winter on the southern hemisphere, right? So it's the tilt of the Earth's axis when the northern hemisphere is tilted towards the sun, the angle of the sunlight is steeper, more sunlight reaches the northern hemisphere, and that is what causes the summer then. Okay. If there are no more questions, well, we have no more questions in the quiz. Let's say it like that. So let's get right to the prizes. So you can win if you have more than half the answers right, and then you just have to be lucky enough to be drawn as one of the 3 randomly drawn winners. Then you will receive an email if you put a valid email address, of course. And we will let you pick one of those nice prizes. We have a set of cards about stars and planets. We have a Metal Earth building kit of the Saturn V Apollo rocket. We have a nice notebook by the Euclid Consortium, and we have 2 books by Stephen Hawking, Brief Answers to Big Questions and My Brief History. Also, you can win if you live in Bonn. You can also win it if you don't, but we recommend you don't take it. A Tai Chi voucher at the Sportzentrum Bonn, so you can try out this sport. Yeah, with that, thank you for the opportunity to present this, and I will go back to Felix.
Yeah, well, Felix changed a bit. I also changed my name and my gender, and but this is nothing new in 2021. And I will give you some concluding remarks to this, and it's basically only giving you a spoiler what you will see next event. And I made actually a total amount of 2 slides, so then it's over. And then we all go and have some food, and I don't know what about you, but I guess a lot of us will have pancakes for reasons I don't quite understand. I see Victoria laughing. You can't because you're not in the same Zoom, but I can see her laughing. So just let me give you a spoiler what you will see next month if you join us on the 27th of April, 7 p.m. Central European summertime. As always, we will have Dr. Herbert Nett, and he will actually turn the tables around, because it will not be the Earth observing something in space, it will be observing the Earth from space. So stay tuned. That sounds very, very interesting. And then we will have Manali from our AUT Bonn team, and we will make a very, very cool interview style, maybe something with asymptotic giant branch stars. Let's see. I was not supposed to tell you this because she didn't decide. So you don't have it from me, don't tell her. And that's it. And I hope you had fun. I had fun.